Hello students, in this video we'll discuss about intermediate representation and variants of syntax tree. So first where we are, so in 7 phases of compiler we have already done with the first 3 phases, that is lexical analysis, syntax analysis, it is nothing but parser, and semantic analysis, it is nothing but type checker, right? So here the tokens are given as input to the parser and that will be check whether it is syntactically correct or not, and it will generate the parse tree, and this parse tree will be given as input to the type checker and it will give you semantically verified parse tree. And then the intermediate code generator represents the code in any intermediate representation. We have some popular intermediate representation that we'll discuss later, and then the code will be given to the code generator. So from this phase onwards, code generation is completely machine dependent, and we can also call it as backend. Until this we can say that it is front end or machine independent phases. Then what is the need of representing the code in IR? Why should we do it? See, first benefit is retargeting. Assume that you have written a code for some program, okay? So assume that we have written the code for add.c in Windows language. Then what will happen if you compile, right, with the first 4 phases, lexical analysis to intermediate code generator, then the add.c will be converted to some intermediate representation. Let me take this add.ir, just assume that. Then after that will be given to code generator and it will give you the target code like add.s, okay, the symbolic code or assembly language code. Now see guys, this code is machine dependent, right, and this one is machine independent, and this one is machine dependent. We are targeting a particular machine, and this one is machine independent. Then assume that we have written the code in Windows, but one of my friend wants to execute the same code in Linux. You cannot take this as it is machine dependent, and you can take this, but again you have to undergo with the lexical analysis to intermediate code generation. It takes some time. So that's the reason what I'm doing here. I'm taking the add.i, the intermediate representation, then I'm giving it to the target code of the Linux operating system. Then it will give you some other code, so which is completely dependent on Linux. Same way, if my other friend is using another operating system, right, then you can take this add.i, but again you have to execute the 4 phases, and you cannot take this as these are machine dependent on Linux and machine dependent on Windows. Now you can take the intermediate code and you can use the code generator will give you the add.asm for that particular machine. So this is same source code can be retargeted to more than one machines, called retargeting. And same thing you can apply it for the compilers also, right? See, for example, you are developing a new compiler Mac in C language for Windows operating system. Then again you have to write the code for lexical analysis to intermediate code generator, right? So then later you can write the code for code optimizer, target code generator and all. Then see, once the code is, this is targeting a particular machine, but this is front end, it is independent of the machine. So if you want to write the same compiler code in Linux, you cannot take these 2 phases, but you take the same phases and write down the code for code generator and code optimizer, so that you can think about the machine where you are developing it. So same, that is called retargeting. The name is targeting the same code for different machines. And of course, a machine independent code optimizer can be applied. So once the code is represented in IR, you can apply some generalized optimization techniques which are not meant for a particular operating system. And there are some intermediate representations like abstract syntax tree, polish notation, and 3 address code. And we have another variation of abstract syntax tree called directed acyclic graph. And this polish notation is also called as postfix notation. Okay, general postfix notation. Then 3 address code. So this is the most widely used out of these 3 representations. Okay, abstract syntax tree, it is nothing but a condensed form of parse tree. For example, if you know the precedency and associativity of the operators, then you can simply construct the AST without knowing where we are executing the code. irrespective of its meshing. Assume that according to the C language, plus and minus are having equal precedency, right? And star is having higher precedency. Assume that. So the precedency goes from low to high, and both are having left associative. Means if you have two, the left one will be evaluated first. So means we can say that plus is having higher precedence than minus. So then out of these three, plus, star, minus, which is having the highest precedency? Star, then plus, then minus. So the least precedency operator is minus. So in AST, always the least precedency operator should be the root node. Then what is the left hand side of minus? A plus B star C, and right hand side is only D, you can take it. And out of left hand side, this is the left subtree, A plus B star C, and out of these two, which is the least precedency operator, plus would be acted as a parent node of that subtree, and the left hand side of this plus is only A, and the right hand side of plus is B star C, where the operator should be occurred as internal nodes, and you can take here B and C. So this is how the abstract syntax tree will be constructed. So once you have constructed like that, you no need to worry about what is the precedence and associative of the operators. Even though minus is having higher precedency than the plus in some other machine, but according to the user, the minus has to be evaluated last. Once it is represented, we are done with that. Then coming to this, so how to generate this syntax tree, abstract syntax tree? We have any SDT for it. So of course, while you are representing the code in intermediate form, you have to execute this SDT, the grammar productions and the actions. For example, let me take a simple example of, okay, so ID minus ID plus ID. So same thing you can take here, whatever we have taken, or if you want to go with another one, so that's your wish. Then let me construct the parse tree for it. First you have to do that. So E tends to E plus T, and T tends to ID. Same way E tends to E minus T, and T tends to ID. The ID is nothing but 4, right? And E tends to T, T tends to ID. That is nothing but, okay, some symbol, you can take it, ID minus ID plus ID. Then how you have to do it? So what is the first action rule to be evaluated here? So T tends to ID. Then what we have to do? T tends to ID. Create a new leaf node with the ID and entry. So what will be happen? We have to create new leaf node. So here we are going to have the two things, leaf nodes. One is ID, and what is the number for ID dot entry. Okay, so assume that if it is A here, B here, C, then you can take that the entry of A, right? And this address is stored in T dot node. The address of this will be stored. For example, if it is 100, that 100 is stored in here, T dot node, means here we can say that the 100. Then same way E tends to T, next one, according to the SDT I am telling. Then what will be happen? E dot node equivalent to T dot node. Here it is 100. Then next you cannot evaluate this without this. So T tends to ID. Again what you have to do? Create a leaf node with the ID and ID dot entry, and address assume that 200. It is B. Assume that. So this is 200. And what is the next one to be evaluated? E tends to E minus T. What we have done here? So we have to create a new node. Of course, we have to create a new node with what? Minus as its node, and left side is E1 dot node, means the child 100. So here it should be 100, means the link will be established to this. And right side is T dot node. What is T dot node here? 200. So here 200 means this is a pointing to this. So same way, next one, T tends to ID. We have to create a leaf node with the ID, and entry is C. And assume that this is 300, that will be stored in T dot node. It would be 300. Then the last one to be evaluated is this, E tends to E plus T. What it is? Create a new node with plus, and the address of this is E1 dot child. What is the E1 dot child here? We have created, right? So the new node, whatever we have created, that will be stored here. So assume that this is 400, so that will be stored here, because we didn't mention that 400 earlier. Okay, then the child, this one E minus we have created, right, for this. So the 400 will be stored here, then the pointing to this. Same way, T dot 300. See, whatever the parse tree we got here, so that will be generated. So this is about abstract syntax tree. Then what is the another variation of abstract syntax tree? Here we have directed acyclic graph. So in the directed acyclic graph, the common subexpressions would not be taken as more than one parent. It would be combined. Like for example, if I take a plus a star b, assume that we are having like this a plus a star b. So what is the least frequency operator according to the abstract syntax tree? Plus. Then the left hand side of plus is a and right hand side of plus means is a star b, where the star is taken as a parent node and a and b. So according to this rule, it is nothing but the nodes, right? We are creating the double linked list nodes. So what is the need of taking it? So this is the AST. Instead of creating the node for every variable, we can take it from the already existed. Like see, for example, we are having star B and A, and this plus left side is nothing but pointing to the A node. Already the memory is allocated for this A, right? What is the need of again allocating the memory for A? Instead, you can make this as a child to the plus. We can make this A as a child to it. This is called directed acyclic graph. Means what we are doing here, simply we are taking more than one parent for a node if it is common subexpression. In this case here, the abstract tree, let me construct. So here the least presence operator is plus and the left hand side of plus is star, the least because minus is kept in the brackets. Then we are going to have D here, then automatically minus B, C. The left side is done. And right hand side of plus, we are having A plus A star B minus C. The least is plus, then A, and the right side is star, okay, then A, and minus B minus C. The rules of AST. This is the AST. But see guys, here in AST we have so many common subexpressions like A and A. So you can make one as same parent. So automatically it will be created. And see the B minus C, the complete common subexpression. So instead of creating a node for B, C minus, then you can simply take this subexpression as a parent here. So you can take like this. So this will create a directed acyclic graph. So the common subexpression should have more than one parent. So another one, the Polish notation, and we can also call it as postfix. So now see, you know about that. We are going to have, if it is like operator, operand, operator, and operand, okay, 2, 1, then this is an infix notation. Then in postfix, we can call it as operator, right, should be at the end. So you have to take operand 1, operand 2, and we should write the operator at the end. So this is called postfix notation. So what is the advantage of it? Why should we do it actually? And you might have discussed about the postfix notation earlier, right? Why should we represent the code in postfix notation? See guys, here what is the least frequency operator? A plus B star C minus D. Actually, without parentheses, the minus is the least one. But as we kept in the parentheses, so we are giving the higher precedency to the lower precedency operators. Then, and you should know, to evaluate this expression, you should know the precedency, you should know the associativity, and you should know the you should use the higher precedency operators within the parentheses, right? Then once the code is represented as postfix notation, like for example A plus B star C minus D, right? Once the code is represented, right, as a postfix notation in this case, then you no need to follow the precedency and associativity of the operators. If this code is given to any machine, right, any machine, here we are not specifying what is a higher precedency operator and what is a least precedency operator. So how to evaluate this postfix notation? We can use the stack and you can evaluate it. So that is the advantage of representing the code in Polish notation or postfix notation. And the final one, the most widely used, is 3-address code. See, the 3-address code means at most 3 operands are allowed. So how we can represent this code in 3 addresses? So, and the next concept of our concept is 3-address code only. In that video, we'll clearly discuss about this 3-address code, how this code is represented. That is 3-address code.